This video is on reaction mechanisms, or mechanisms of reaction. So, as we've done before, like with thermochemistry, a lot of reactions occur in a series of steps. So, not just one step. So, here's a series of steps. We're going to try and figure out, first of all, what the overall reaction is, going on. So, the first thing is this stuff turns into these. The C4H9 that was made in this reacts with water to make this. This product comes down here, reacts with water, and makes something here. So let's figure out what the overall reaction would be from this, just like we've kind of done in the past. So first thing, C4H9 with a positive charge is made here, and it's used over here. That's called a reaction intermediate. That's going to be important. This is called an intermediate. It's made but then used, so it's not going to be in the overall reaction. So again, that's called a reaction intermediate. Same thing with this substance. It was produced in this step and used over here, so the net is that there's none there. It's an intermediate. It's part of the series of steps. It was there for a little bit, but not there in the overall reaction. So everything else should be okay. Nothing else canceled out, doesn't look like. So our overall reaction would be 1 molecule of C4H9Br reacts with 2 waters to make 1 mole of Br negative plus a mole of C4H9OH, this substance, plus a mole of H3O plus ions. So there's our overall reaction. Now if we look at our steps here, this step, it says, is slow, and the last 2 steps occur very quickly, very fast. It tells you that they're fast over here. A reaction can't be any faster than the rate determining step, which is the slowest step. The reaction can't go any faster than this step. So this is called the rate determining step. The slow step is called the rate determining step. This step determines the speed of reaction. Down here, our intermediates, again, we said were the things were crossed off there. So we'll come back to that rate determining step here in a second. Question down here at the bottom asks if X is a catalyst. So if there was a catalyst in this reaction, not all our reactions have catalyst. If there was a catalyst, put it in there. Well, if there's a catalyst, it would be here, if X was a catalyst, and it would be there. So a catalyst, remember, is not used in a reaction. It's not consumed at all. It's put in and comes out the same. Remember, catalyst, all it does is lowers the activation energy, speeds up the reaction. It lowers the activation energy of the reaction, doesn't take as much energy to make the reaction happen, makes it go faster. So if there was a catalyst in there, it would be there and there. A lot of times we'll see catalysts in a reaction. Again, they will not be part of the overall reaction. Going down here, sketch a possible reaction coordinate based on the mechanism given without the catalyst in there. So if we do that, this is just showing the energy pathway, which we haven't done a lot of, but this energy reaction going there. So we do this, let's say that these are our reactants. Let's say our reactants start off with this much energy. Well, the reaction happens in 3 steps. And the first step is the slow step. So the first step probably has the highest activation energy. I don't know how low these go. And then the next 2 steps were slower, so they must have smaller activation energies. Maybe these are products. So from here to there is called the activation energy 1. Here's something I'll write is EA1. That's activation energy for the rate determining step. Activation energy 2, activation energy 3. So the slow step is this one. Now, I drew the products and reactants almost the same energy. If the products had less energy, then it'd be an exothermic reaction. If they had more, it'd be endothermic. Now it says draw it with a catalyst. So if a catalyst is present, all a catalyst does is lowers the activation energy for the slowest step. So if we had a catalyst in there, now it might look like this, and then maybe stay the same. So if we had a catalyst, it would lower this activation energy to only be that high. So it lowers that activation energy to that. Now, when we write our rate expression, it's always based on the rate determining step. Okay, our rate expression is always based on that, right? Which we'll come to in the next part. Next part, determine the correct mechanism for the following reaction and rate law. Okay, correct mechanism for the following reaction rate law. So, first of all, here's the overall reaction we want. Okay, overall reaction we want 2 NOs plus 2 H2s to make 2 waters plus N2. So we need to make sure that this does that. We want it to be second order for NO and first order with regards to H2 for our rate law. So our rate law is that. So if we look at this, let's get rid of any intermediates and any catalysts if there's any there. So N is produced, N is used, that's an intermediate. N2O is produced here and there. Okay, so our overall reaction is 2 NOs plus 2 H2s forms 2 waters plus an N2. So this is the correct overall reaction. Now, this is the important part of this stuff probably. Our rate law, our rate expression is based on the slow step. Okay? And when we have individual elementary steps for reaction, we can go by the coefficients for our orders. Okay? Only when we have individual elementary steps of reaction, we can go by the coefficients for orders. So since this is a 1 coefficient and a 1 coefficient, we can write rate equals K, concentration of NO, times concentration of H2. Both to the first power. Okay, both to the first power in that situation. Well, our rate one is supposed to have NO to the second power. Here it's only to the first power. So again, we usually can't do this. Only when we have these elementary steps can we say our coefficients equal that. Again, the slow step is what we base our rate expression on, or our rate law on. Slow step is based on that. So this mechanism is not right for this. Let's go to the next one. Mechanism 2. It's the same thing. Let's cross off of our intermediates. Sorry about the glare. We got N, N2O, N2O. I think we're good there. So we got 2 NOs plus 2 H2s makes 2 H2Os plus N2. So our overall reaction is correct. That's what we want it to be, just like it was the top. Our slow step is now this one. Okay, slow step is this one. So if I write this, this is going to be a little tougher one, so you got to really pay attention here to what's going on. If we write, okay, rate equals K times the concentration of NO to the first power, okay, is our slow step. There. So on this, okay, our slow step is there. The formation, NO times N to the first power. Sorry, our slow step is that, okay? So our slow step has these two things, N and NO both to the first power. Well, this is an intermediate. Intermediates cannot be part of your rate expression or your rate thing. Intermediates cannot be in there. So the formation of this is formed by these. So this being formed is dependent on those. I'm going to substitute, for this, I'm going to substitute these two things in. So for N, I'm going to substitute NO. I'm going to substitute H2 because this intermediate being formed, that was part of this, is dependent on those. So I'm going to replace it and go, okay, well, we have K, concentration of NO, which was there. And replace this with NO to the first because it's a 1 out front, times H2 to the first. Well, now we have NO times NO, which would be NO squared times H2. So our rate equals K times the concentration of NO squared times concentration N2 to the first power. So whenever you have an intermediate that's part of your rate determining step, you got to substitute in for that intermediate. All right? This does match our rate law we had at the top of the page. All right, we'll do some more of those. Hopefully that makes some sense.